Okay, great. So thanks a lot for the kind introduction. And yeah, as you've already heard, I'm going to present the software package cashocs for PDE Constrained Shape Optimization, PDE, because we're at the Phoenix conference. And I'm going to show you a bit what you can do with this. So first of all, some industrial applications which we are working on or which I've taken from the literature. You can think of many optimization targets which you want to optimize, like car design or aircraft design. We are looking at chemical cells or continuous flow reactors. And also historically, my department has been active in spinning processes, and I will show you some applications for this too. So what all of this has in common, it's if applications are coming from industry, they're quite complex, and we need efficient solution algorithms that can easily be applied to tackle these. And if you're familiar with shape optimization, you will know that in recent years there have been many developments to facilitate such efficient solution algorithms. For example, the work of the group of Volker Schulz and so on. And we have also done some work in this direction. And today I will present you cashocs, which implements many of these things and makes it easy for you to use. Okay, so first of all, what is cashocs? It's a general software. It stands for computational adjoint-based shape optimization and optimal control software. And so it can tackle optimal control and shape optimization problems. And recently, it also got the ability to tackle topology optimization too. So it's based on Phoenix and finite element method, of course, and it's basically built on top of that. So, and when I talk about Phoenix, I'm talking still about legacy Phoenix, because we will have to do a port of this once the new Phoenix X will be stable. It's open source. You can just use it, hop on GitHub, get the code. And we have also an extensive documentation, so over 30 demos, so you can get started quickly, I hope. Yeah, and we talked a bit about remeshing, so that's also pretty nice, because for complex problems, shape optimization, the meshes will deteriorate, so you will need remeshing for practical problems. That's also automated, and we also have full MPI parallelization, so everything you can run there can be done parallel, and that is, of course, extremely helpful for complex problems. Okay, so for those of you not so familiar with shape optimization, here's briefly the idea of what you need to do. You have some problem which depends on the shape of a geometry. Like I'm not talking about discretized things here, that's totally continuous. You change your shape a bit, you perturb it with some somewhat regular deformation, and then you compute sensitivities based on this. And with this, you get a shape derivative, which gives you sensitivity information, and this you use to define a so-called shape gradient or gradient deformation, which you use in optimization algorithms. And then you can think of gradient descent methods, quasi-Newton methods, and so on. Okay, so how do we get this for PDE constrained optimization? Well, in a previous talk, we have already seen a bit of this. So here I've just written down formally the adjoint approach for those of you not so familiar with optimization. So you have some problem, have a PDE constraint, and then what you do to compute the sensitivities is you introduce a Lagrangian function, you basically add the cost functional and the PDE constraint, and then you take derivatives in order to get some equations, like the state equation you already know, you get some adjoint equation, and then you project your shape derivative to get some gradient information, basically. So the big part is that if you think about complex problems, you will need complicated equations. You will need systems of coupled equations. And so you add equations, basically, which are coupled, and then you have to do all the math. And you will see this gets messy really soon, really fast. You will make lots of mistakes using the chain rule to do so. So it's really error-prone and tedious to do so by hand. So, and now the nice thing is, and we've heard about this in the previous talks in the first session, basically UFL. Because when I started implementing this, I worked by hand and I used Phoenix to solve it. And what I've seen is basically state equations, when we talk about theory, they are always some weak forms, variational forms of PDEs, right? They are represented in UFL. Cost functionals usually involve some integrals over state variables. That's also done in UFL. And the most important part is that UFL is so extremely flexible, at least for my purposes, I found. You can add UFL forms, you can concatenate them really nicely. And what's important, you can differentiate them, which is great to solve nonlinear problems, but also great to derive adjoint equations. And basically what cashocs does is it builds on top of that. You supply your forms for defining your problem. And then in the background, there will be an implementation of the continuous adjoint approach, building that Lagrangian and differentiating it to get all the forms you need for your problem. Okay, and so to show you a bit and to convince you that it's really easy to apply, I have kind of the so-called mother problem for, I mean, that's usually the mother problem of optimal control. I adapted it for shape optimization. So just some cost functional constraint with a linear Poisson equation. And it looks basically like you would use Phoenix code, right? Just going over it briefly, you import from Phoenix and you also import cashocs. Then I've written some import function which defines my mesh, boundaries, subdomains, and so on. You can do that manually too. It will work, but I found it easier to do so. You define your function space, like piecewise linear Lagrange elements. And you define usually your function for nonlinear problem. I will come back to this in a minute. And a test function. You define your right-hand side, define your PDE constraint, and your boundary conditions. Okay, so now we have the PDE. That's basically all you can do just with Phoenix. What we need too is the cost functional. So that's basically, it's just a wrapper, and it's used to implement more abstract cost functional classes. So basically what you do is type u times dx to have an integral over u over the whole domain. Nothing fancy here. You can do that with Phoenix 2. And now the only thing that you need to do is basically change 2 lines of code. The p here is a test function now. Due to the way that UFL works with differentiation, you need to change it to a function, and then you need to define your problem and call the solve method to solve it. And you can change the algorithms, whatever you want. You can do here, specify tolerances, and so on. So that's really nice, and I found it nice to stay in this simple language that Phoenix provides already. Okay, now that I hopefully have convinced you that it's really easy to apply, let's take a look at some industrial applications which we've used cashocs for to solve. And I'm going to name a few, like we have used it to optimize flow fields and electrolyzer cells. We have considered microchannel reactors, continuous flow reactors in general. We are working on the field of synthetic fiber production, and also for diffusers of airflow. And just 3 quick examples. So what we've done here is we considered multi-criteria shape optimization of flow fields, which are part of electrolyzer cells, where we have used cashocs to get optimized shapes, which will distribute the flow more evenly and get rid of some bad dead spots, which can occur. And yeah, that's joint work with another Fraunhofer Institute, where we currently have made a suggestion for them, and they are finishing or manufacturing these optimized cells and trying to experiment on them to see how well the theory really works. I have also another example where we consider synthetic fiber production, where you use a molten polymer. You can think of it like a shower head where water comes out. It's just now molten polymer, flows down, and you have to cool it to produce the fibers. And what you do is you blow air from the side. And what you want is that all fibers get cooled evenly or get cooled better, because as you see on the left figure, there's a standard spin pattern. You will get worse cooling in the back rows. And what we've done is we went from free-form optimization back to parameterized shape optimization. Here, got an optimized pattern which introduces lanes so that the air can really flow to the back rows, and optimize this. And also another nice application, we're working on this with colleagues from the University of Ulm. They have packing columns for distillation processes. You can see some 3D printed packing column here and a CAD geometry. And for our optimization, well, they provided us with some model which works nicely. It's a one-phase model. We considered the flow and mass transfer in these packings and optimize the shape so that we get a higher mass transfer, which will hopefully also increase the distillation quality. And we were able to get an increase in mass transfer by about 20% with this. And so here it's just, you cannot really see it too well, but with minimal geometric changes, we are able to get this increase in mass transfer. And it's really nice because it's a complex 3D geometry with several tens of millions of TEDs, which we have been able to optimize using cashocs. So, and with this, I think my time is nearly over. So yeah, I have shown you cashocs, hopefully convinced you that it's really easy to apply and that you can check it out. And also I've shown you some applications where we use cashocs to solve them. And here are some literature if you're interested in this. And with this, thank you very much for your kind attention, and I hope you have some questions.